Swayam Prabha. Digital India. Educated India.
This is the concluding lecture for the course, and I will try to give an overall perspective of the different things that we have done, so that rather than talk about the details is something you have to go through. That is what we have done in this full course, looked at the details of how to solve equations, how to formulate problems. And so today I will just try to give you the full picture, so you know what the different pieces are that we spoke about and how they are connected, and so then you can worry about the details. So macro picture, micro picture, two things. Okay. So we have been dealing with all the micro analysis so far, so now we will give that overall perspective. And idea is, I hope some of you will possibly work in this broad area of transport phenomena, maybe experiments, maybe simulations, and some of the things I will tell today will help you. Okay. So like I said, we have two ways of solving a problem, right. We use the Eulerian approach or the Lagrangian approach. So that is what we spoke about right at the beginning, and I have to give some name to this lecture. So I am going to call this overall perspective. Okay. So everything that we have done has a mathematical significance and has a physical significance, and idea is you want to understand both these aspects so that you can get a better picture, better comprehension of whatever you have done so far. Okay. So for example, you spoke about Eulerian and Lagrangian approach. The one which is most commonly used, okay, in solving fluid flow problems is the Eulerian approach. Here we focus at a fixed point in space, and here we focus on a particle. So basically the particle is going to keep moving around, okay, and so any changes you are looking at is going to be changes in the property temperature, for example, because of change in time and change in position. Here it is only because of change in time, because it depends only on the it is at a fixed position. So there is no question of variation of position. Okay. So this we say, I mean mathematically this is a partial derivative and this is total derivative. And you can extend this for a finite control volume, okay, and we did that and we came up with the Reynolds transport theorem. So I mean this is what we did. It is basically extending the relationship between Eulerian approach and Lagrangian approach. This is extending the above to control volume and control mass. Control volume, we did not complicate things by making the control volume change and move. So, we said control volume is fixed in space. So, that is the Eulerian approach, and control mass is the Lagrangian approach where you are looking at a fixed mass. Okay. So, that is basically the thing. And why do we need to do this? Because most of the conservation laws are in terms of the Lagrangian framework, in terms of control mass. Your conservation of linear momentum, Newton's law of motion for example, is for fixed mass, but we normally are going to use Eulerian. So, we have to make that relationship, change from Lagrangian approach where the laws are applied to Eulerian approach, which is going to tell you how things are changing at fixed point. Okay. So, most of the fundamental laws like conservation of mass, momentum are in the Lagrangian framework. So, if I say mass cannot be created, mass cannot be destroyed, dm by dt is 0, that is only for control mass, that is not applicable for control volume. Okay. And we are interested in how things are changing in control volume. Okay. And our interest is in changes in CV. Okay. And hence we need to relate these two. Okay. So, that is what we did. And just to put things in perspective, I mean the Reynolds transport theorem is just another way of looking at the conservation equation that you are familiar with, where you say accumulation equals in minus out plus generation. Okay. So, you are comfortable with this. Okay. And this is changes in a control volume, this is mass influx, and this is changes in control mass, the generation term. Okay. So, I think you need to understand how they are the same. For example, if you have control mass, this generation term we put it equal to the reaction rate term in case there is a reaction. Okay. Because although you have a fixed mass, because of chemical reaction, A can be generated, one species can be generated or a product can be generated, reactant A can get consumed. So, in that generation term you can have changes in the concentration because of reaction. So, this is like your reaction rate term that you have, and this is the CSTR will be in and out term, and this is the accumulation term inside the reactor. Okay. So, I think once you understand that, you will get more comfortable with Reynolds transport theorem. The other thing is normally we are working with the Eulerian framework, but there are some problems where you will prefer to work in the Lagrangian framework. For example, recently we saw the Taylor dispersion problem, okay, where we use the Lagrangian framework to find how the spread of temperature and concentration takes place. We are writing in terms of this effective diffusivity, effective thermal conductivity. Okay. So, although so basically depending upon the problem, you need to decide which approach. The other problem where we used something like a Lagrangian framework was in the Stokes flow, where we had the drop falling down and we calculated the drag force. Okay. So, actual problem is liquid is stationary and the particle is moving. But we looked at the opposite problem where the particle was stationary and the liquid was moving with a relative velocity in the opposite direction, okay, because that is much easier to solve, because now if you do the problem in the Eulerian framework, you have to track how the particle is moving. If you do it in the Lagrangian framework, you are sitting on the particle. So, as far as you are concerned, particle is stationary, but the liquid is flowing with a relative velocity far upstream, okay. So, depending on the situation, you may want to use the Lagrangian approach also. It is not that you always have to use the Eulerian approach, okay. So, we can use, think of we use Lagrangian approach for the sphere falling in a liquid, okay, and the last problem was the Taylor dispersion. This is an easier approach, okay, for these two problems. So, for these two problems, I mean, we changed. So, there are no hard and fast rules, you need to decide what you want to do. And from the Reynolds transport theorem, what we did is we derived the equation of continuity and the Navier-Stokes equation, okay. So, that is what we did, we just allowed that control volume to shrink, and we looked at the Eulerian term, flux term across the control surface, and the material derivative we represented by force, for example, and then we put in the viscous force, pressure force, gravity force, okay. That is what we did. So, from this the RTT, we derived the equation of continuity and the Navier-Stokes equation, okay. And basically that generation term which is associated with the control volume for momentum, we replace it by the forces, rate of change of momentum of a control mass is equal to forces, and then we brought in the pressure and the viscous term, that is what we did, okay. For the generation term, rate of change of momentum in a control mass is equal to forces, and these are what bring in the pressure, viscous and gravity, okay. That is how, I mean, we got the Navier-Stokes equation. So, I mean, we actually, you may not be able to see how we went from one to the other, but that is the connection, Euler, Lagrangian, Reynolds transport theorem, and that is what I said, we have to represent the Lagrangian approach to the Eulerian. That is what we did here, which we possibly have to understand is the governing equation for the, let us take the example of the Navier-Stokes equation, okay. The Navier-Stokes equation is given by du by dt equals minus gradient of P plus rho g plus divergence of tau, okay. And for a Newtonian fluid, you write tau as gradient of u plus gradient of u transpose, because it is symmetric. So, this is the Navier-Stokes equation. this equation is a very general equation. It is valid for any coordinate system, okay. But this equation in this form is quite useless. You have to convert it to the specific coordinate system that you are interested in, depending upon whether you have flow between flat plates, then you will use rectangular Cartesian coordinates. If you are looking at flow over a sphere, then you may want to go to spherical coordinate system, and then you have to look at flow over a cylinder or something, then you may want to look at working in a cylindrical coordinate system, okay. Then we were looking at how to represent each of these terms. This term will have du by dt plus divergence of rho uu, and you saw what that subtle difference was when it comes to these different coordinate systems. I mean, one main issue or main difference was, in the Cartesian coordinate system, the unit vectors are always in the same direction, they do not change from point to point. Whereas in the spherical coordinate system and in the cylindrical coordinate system, the ER and E theta will vary with theta, okay. And because of that, when you evaluate these terms, this term and this term, you get additional contributions like the V theta squared by R, okay, term, the centrifugal force term, V theta VR, some Coriolis force. So, therefore, and what we were focusing on is how to derive these expressions in the different coordinate systems, okay. So, my main objective was that you should be in a position to derive the equations that you are using, okay. And I mean, you can take the cylindrical coordinate equation given in a book and use it, but you should also know, I mean, you should have the curiosity to ask, why are these additional terms coming? For in the rectangular Cartesian coordinates, you do not get those additional terms, right. So, only in this other coordinate systems you get extra terms. In the Laplacian is different, divergence of tau is different, divergence of rho u is different. So, I mean, you can get along with your life by just looking at some book where those equations are and you can use it. But I think if you are specifically going to be doing research, and you need to have that curiosity to ask the question, how did this term come, okay. Cartesian coordinate is different, this coordinate is different, and you know, try to get into the basics of it. And when you do the basics of it, I mean, we spoke about how to find tau, we spoke about how to find this, and you know, we did some problems where you had to calculate these quantities, and then you saw how those additional terms are coming, okay. So, at the end of the day, you are going to use the equations in the respective coordinate system, because this equation is completely useless, although it is absolutely correct. So, for solving a problem, you need to use to solve that problem with appropriate boundary conditions, okay. So, basically we saw how additional terms come in cylindrical and spherical coordinates, and this is because the unit vectors are changing. For example, in cylindrical coordinates, d by d theta of E theta and d by d theta of ER are both not equal to 0, and that was the one which was giving you the additional contributions, okay. And this occurs everywhere. I mean, we spoke about how to handle tensors and all that, right. I mean, tau, for example, we wrote as gradient of V plus gradient of V transpose, and gradient has this derivative operator, okay, and V will have VR ER. So, when you differentiate with respect to theta, you use the product rule and do the differentiation, okay. and then you get your extra terms which come up. So, I mean this understanding is what I was trying to develop, okay. So, you could idea is, I mean if you can derive these equations the way I try to do it, tomorrow when you read a paper, okay, and you see an equation, you will not be intimidated. That is the idea. I mean most of you are masters and PhD level students. So, you may be doing research in this area where you have not only in this context, not only in transport, any other in reaction engineering, whatever it is, you will have, I mean if you are interested in modeling, you will have equations and you should understand how those equations are derived from first principles. And normally what I would expect is that you would possibly derive it once, derive a second time, third time, then possibly you will get more comfortable, and that is to me is very important, because that will give you more confidence about what you are doing. I mean rather than just use something. So, when you go for a presentation, when you go for a seminar or whatever it is, your body language will be different, okay. So, you need to put in that practice of deriving equations, and PhD students who work in this area, they keep deriving same equations, they will be deriving 25, 20 times, 50 times till they are, to make sure that they have not made any mistake and to get confidence, okay. So, I mean that is the minimum thing that is expected, I mean especially if you are doing research in this area. So, you should not be lazy to do this derivation and all that. I mean like I said, it gives you confidence. I mean these days IPL is going on, I mean I do not know how many of you watch, but I mean those guys who are going there and playing, I mean surely they are not just going to the field and playing, they are practicing for days together, months together, hours together, and that is what allows them to go there and perform, good or bad, they are at least able to stand there and play. So, if that guy can put his practice in this, and this you are not playing the IPL, you have to derive equations, okay, keep deriving equations, and hopefully you will be an expert in deriving equations and making presentations. So, I mean anything you want to excel, any sport, anything, it requires a hard work to put in, okay. And I basically spend time deriving, I have never used the PPT in my life, so I do not want to use it now, but one of the reasons why I derived every equation as far as possible was to tell you that it can be done, and that if you are willing to spend time, you will also be able to do it, okay. And I think that confidence you people have to have. I mean I can go and put a PPT and slide and show this is happening, that is happening. I do not think it is going to be as effective, because things like this course you have to go step by step, go slow, so that you can catch up with me. Otherwise in a PowerPoint you are just going so fast, nobody understands anything. So, that was the specific purpose for not using any slides, and I do not believe in slides. Of course, if there are some times you need to have slides, because you do not want to write these equations, some equations are very big. So, I do not expect that you should be mugging up all these equations, okay. It is not necessary, because these days most of the tools are available in the internet, in books, but if there is an equation which comes, some questions have to be triggered in your mind as to what that equation means, what the terms mean, and how do you go about solving problems with those equations. Then what we did was we looked at a couple of problems, I mean couple of things which is not normally done. Supposing, because most of the time we look at boundary conditions, okay. Just to tell you what we did, most boundary conditions we apply to are on iso coordinate surfaces. What do I mean by iso coordinate surfaces? That means that coordinate is a constant, it will be r equal to constant, it could be y equal to constant, okay. So, for example, y equals h or r equals capital R, this is the coordinate and it is constant on the surface, Okay. This is an example. So, the coordinate is constant. Okay. But there can be problems where you have a surface where the coordinate is not a constant, coordinate is a function of another coordinate. Okay, we saw that. For example, like we did this problem, what if we have a surface which is of the form, let us say r is equal to f of z. R is not constant anymore. Where will this kind of a problem arise? Supposing you have a jet of liquid falling down, this is R and this is, let us say, Z. So, along this surface, R is equal to f of z. So, so the physical quantity is the same, the tangential stress is 0, or the normal stress is balanced by the pressure, something like that. Okay. So, you need to, I can't use what I use for isocoordinate surface anymore, because physically that is coming from how the tangential stress is defined and how is the normal stress defined. So, for that you need to figure out the normal to the surface n, the outward normal to the surface n. And again, maths, whatever you did in your calculus course, when you have an implicit function, n is defined as gradient of f by this. Find the tangent which is going to be perpendicular to it. Okay. And you need to, you can't just say tau xy equal to 0, because that is only valid for constant coordinate, because now the normal is changing. You say that tau nn, the normal stress, is going to be given by n dot t dot n. This is the stress tensor, and you have tau nt, which is the shear stress, and given by n dot t dot t. Okay. This is the normal stress. Again, I mean, there are many papers you will see, I mean, the boundary condition will be not the usual du by dy equal to 0. Du by dy equal to 0 is only for when the interface is flat. Okay. You will see maybe a complicated expression, but physically he is doing a shear stress balance or a normal stress balance. How do you calculate the normal stress? For a surface, this is known, T is known, tau xx, tau xy, tau xz. Okay. This is going to be given by your calculation of the from the surface. Okay. And then you use it and you do the dot product. So, I mean, depending on the problem, you will have to use that. So, basically you are, I think, equipped with sufficient skills to be able to formulate problems. Okay. So, idea is you need to be able to formulate a problem. So, that is the reason we looked at different possible problems, you drag force on a sphere, what did we look at? Then we looked at some heat transfer problem where you have the pipe being heated in the wall, through the wall, and the fluid is getting heated, the grids problem. Then we looked at drag force on a drop. Okay. But idea, what you have to do is you have to understand the similarities between these problems, then I think your understanding will improve, not treat each problem as a separate method. I mean, because now at the master's and PhD level, you will try to get the connections between apparently different problem, how this drag force on sphere problem, how do we formulate that problem and how did we formulate this problem? We were using the same Lagrangian reference frame, but the boundary conditions were different, and because it is a fluid, there were internal circulations. So, we had to solve for the flow inside and flow outside. Okay. And what you should be more confident about formulating these problems is, I mean, today you are living in an age where you have all this information. I mean, MATLAB, all the software codes, and some of the problems that we discussed have been solved maybe 100 years ago or 200 years ago. Okay. I think the Rayleigh Plessé was solved anyway sufficiently long time ago, when they did not have MATLAB or Mathematica, all these software tools. So, if they could solve all those problems without any of those tools, you should be able to solve definitely those problems with those tools that you have today, and maybe even more complicated problems. Okay. So, I think you keep that in mind, that most of these classical problems that we have discussed in this course are basically from this thing. So, you are in a much better position. So, but you have to learn to use these tools properly. So, idea is, first formulate the problem, then solve. Formulate means write the governing equations, and you make some assumptions like is fully developed, not fully developed, axisymmetric, there is theta symmetry. Okay. So, maybe simplify the equations with things like axisymmetry or fully developed assumption. And that is what we did when we talked about flow of two liquids, one liquid over a flat plate or between two plates. So, you simplify because you want to be able to get a handle of it, but then again when you simplify, you do not want to simplify too much. If you simplify too much, then you may get 0 equals 0 as the answer. If you put everything as 0, right hand side already has a 0, everything goes off, then you are not solving a problem. Okay. So, you have to do this judiciously and decide what is important. For example, when we spoke about fully developed flow, and let us say the flow direction was in the z direction, we say there is no change in the z direction. Okay. All the velocity is going to be the same with respect to z, but I do not say dp by dz is 0. You can't blindly take all the derivatives equal to 0, because the flow is being generated by the pressure gradient. dp by dz is the one which is causing the flow. I am having a pressure drop. So, I keep, although it is derivative with respect to z, I am not putting dp by dz equal to 0, I am putting dvz by dz equal to 0. Okay. So, you can't blindly do things, think physically and then solve the problem mathematically. That is something which I wanted to emphasize. Okay. And I think there was a lot of stuff we did regarding dimensionless analysis. Powerful tool, and basically what we want to do, you can use dimensionless analysis without any problem if you are not making any assumptions and simplifications. But if you want to use dimensionless analysis and try to simplify, then you may have to use different scales for the same problem in different regions. Okay, that is what you saw. And for example, in the Taylor dispersion, near the inlet we used one scaling where convection was important. Further down we used another scaling to take into account radial conduction is important. So, if you are interested in simplifying the problem and then solving, then you need to, you do not want to solve the full equation, because you want to be smart. It will be computationally intensive to put in all the terms. So, you want to be smart, and then you would basically have to possibly choose different scales in different regions. For example, boundary layer flow, viscous effects are important near the plate, because near the plate the liquid slows down, but further away from the plate viscosity effects are not important, you assume it is like uniform velocity. So, I mean you have already done all of this, but the fact is different regions in the domain have different important physics, and you have to understand the physical problem to make the simplifications using scaling. Okay. So, and this is not easy, I mean it comes only with experience. So, it is not a one shot, I will choose this as a scale. You may do it, you will proceed and find out it is nonsense, come back and redefine variables. Okay. And although whatever I did looks like is very clear, but when you are solving a new problem which nobody has solved before, then you have to be ready for doing the scaling and rescaling again and again, and then see which is the right scale to use, what is the right term to drop off, so that you get the physical insight about the problem that you are solving. Okay. So, scaling is very important because it gives you physical insight, but it is not easy. Okay. And you need to use your physical intuition, because in experimental observation you see that the temperature or concentration maybe is uniform radially in that profile that you saw experimentally. Okay. Then you want to be able to far downstream, you want to be able to simplify the model, so you capture that experimental observation, and that is what is important. Okay. So, basically different regions may have different important effects, boundary layers we have near the wall viscous forces are important, far away fluid is inviscid. Okay. So, I mean you exploit this and then you solve, and we also saw that in some problems where it is not possible to choose the scales properly, you can use this similarity transformation. Okay. So, for example, if natural scales for position and time are not obvious in a problem, we can possibly seek a similarity solution. Okay. I mean again so you need to understand that particular problem we did, you could solve it using, because those equations were linear, you could solve it using Laplace transform or Fourier transform. Okay. But then this looks like one more method to solve. So, when is each of these different methods that you have learned possibly applicable? When can I use Fourier transform? When can I use Laplace transform? They are basically for linear equations, whereas the self similarity solution can be used even for nonlinear equations. Idea is you should possibly solve, especially if you are doing research, solve a particular problem using 2 or 3 different methods and see if you get the same result. Okay. Because I mean at the end of the day you are doing something new. Okay. And there may be already existing results available. It could be equations, it could be in experiments. So, when you are doing something, you want to make sure you are getting the right result, and for example, sometimes we have problems. We see an experimental paper, okay, the person is getting some results in his experiment, and when you do the same experiment, you do not get the same result. So, then you start wondering what is going on, okay, and you have to figure out why is there this inconsistency. It does not matter, although I am talking about transport phenomena and mathematical modeling, this can be true anywhere, even in experiments it can be true, and several times we feel this. So, we do not know whether to trust that result or trust my result, which I have done 100 times, and in 100 after 100 times I am not getting the same result, okay. So, you need to try to resolve these differences, especially if you are different from the literature. You can't just blindly follow what the other person has said, and especially if you are doing the same thing and you are confident about what you are doing is right, you need to figure out what is the cause for this difference, okay. So, I mean, these are the kind of things you will have to do when you do research. It does not matter whether you are doing in computational, whether you are doing in research, in experiments, okay. And everything there is going to be a challenge, but if you want to overcome these challenges, you need to have a good fundamental understanding of your courses that you have done, thermo, transport, math, CRE, whatever, any elective you have done. So, this coursework I think plays a very important part, okay, and that is what we try to do, give courses which gives you the background, so that you can use that to tackle complicated problems, and that is what every faculty member is trying to do. So, I am also trying to do the same thing, okay. I mean, of course, we have some details. We can solve the Navier-Stokes equation either in the primitive variable form, velocity, pressure, or if it is a two-dimensional flow, we transformed it to stream function vorticity. Each method has advantages and disadvantages, okay. So, whatever you are comfort, and you have to understand that, I mean, you have conservation of mass, conservation of momentum, you also have conservation of difficulty. It does not change. It possibly you are more comfortable with stream function and vorticity, so you do that. Somebody is more comfortable with pressure velocity, they will do that, okay. So, you need to understand, you only change the form, the way you are solving the problem. So, just a numerical technique you are solving, okay. But maybe if you want to understand something about what is the vorticity in the system, if that is the focus, then stream function vorticity may be good, but if that is not of interest to you, you can go. So, depending on what is of interest to you, you choose the method of solution. There is no such thing that this is the only method, but you should know the limitations. Stream function vorticity can't be used for 3D flows. So, then you can do only with U, V and P and W, okay. So, I mean, so this is where I think the clarity in your understanding is coming, it has to come, so that you can use the right method for solving the problem after formulating it, okay. So, I mean, I just thought rather than go back and discuss all the things in detail, that, I mean, you have your notes, you will definitely read and understand it, and since these are lectures are recorded, you can go back and listen to the lectures again, but this business of making connections, and I think that one important point which is possibly not emphasized all that much is in the definition of Nusselt number and Sherwood number, which we saw. When you talk about Sherwood number, although the fluid is stagnant, the species can get convected by velocity, because of the fact that the concentration of this solute and solvent equals 1. The mass fraction of the solute and the solvent is equal to 1. So, if there is a gradient here, another grade is induced, and because of that, to make sure that there is no flux, you will have velocity induced, and therefore, although your species, your fluid is stationary, the species has a velocity. So, that changes the definition of Sherwood number, and most of the time we neglect it. We say that velocity is very small, but there could be problems, like I said, in when you are doing nanoscale fluidics, microfluidics, because the velocity is anywhere very, very small there. So, that velocity component may be important, which you may have to include. At the end of the day, I mean, you do all this modeling, you do all the solutions, you have to make sure it is consistent with experimental results. I mean, you can write all the fancy equations you want, you can solve them, but if the predictions are not consistent or with the experimental observations that your friend is doing in the next lab, then all your theory is useless. Okay? Of course, the experiment could be wrong, that is a different story. Okay? So, anyway, you have to make sure, my point is good research is involving both good theory and good experiments. Then only you will be able to say that you understood the problem properly. Of course, we are talking about formulation and all that. Eventually, you will have to write a code. You have to make sure you are not made mistakes in the code so that your results are reliable. So, I mean, everything is we have just spoken about things where we can get results analytically, but some of these problems you have to solve numerically. Then you have to make sure that the code you have done is right. Okay? So, I mean, that is it.